I'm alive. I'm alive, I swear. I'm sorry, Popo. I didn't mean to leave you hanging, man. All right. Where am I? Where am I? Right. I'm trying to get something to work here real quick. Why is it? No, like. All right. All right. Let's try a new. Sorry, this isn't working for some reason. I'm trying to figure out why. Of course, it isn't working. New window capture. Okay. Select a window. OneNote. There we go. And then. No, I wasn't quite dead. I was just trying to get some tea going. All right. All right, we're gonna hop over here. Turn these off. There we go. Sorry about that. I didn't mean to leave you hanging there for a little bit. Just trying to make sure I can get all the stuff working here. So I'm still mucking around with this a little bit. How are you doing? Things are going well for you. How's your school doing? Oh, for frick's sake. Nope. This way. There we go. Okay. Nope. You. Yep, there we go. No, that's not what I want. That one. No. We have to move this a little bit. And then move it a little more. Sorry, I'm just back on the exams, huh? I remember I guess it was the last year, huh? How'd that school go? Hope it went well. Hope you got what you needed out of it. That's a little better. And then the other side is over here. Try to make this work a little better. There. Okay. Hey, Zess. Thank you. Yeah, no worries. Feel free to come and go as you please. There's no oh my god. I keep clicking on the wrong thing here. Just trying to make this more readable. Let's just do that. Let's just do it this way. It'll be fine. There we go. Now it's nice and readable. That's what we want. All right. So, let me just kind of give you an overview of what I want to do on this stream. Popo, you've seen me go up, down, and sideways with some of these plans and some of the ideas I want to do. I've decided to try and be a little more concrete about what I'm trying to do with this. So if you remember, my overarching goal was to try and apply what are they called? Path integrals, right? To Wigner distributions, which is done in certain types of certain aspects of quantum mechanics, and to go from there. You know what? I still don't like that. Let me see. Is that a little easier? That's a little easier to see, huh? That's a little easier to see. Anyway, so yeah, the goal was to like combine path integrals in, or explore how to do path integrals in the Wigner distribution, and then use the Wigner distribution's connection to other types of function spaces. They're kind of these frequency time representation function spaces that are all sort of interconnected with each other. Right. And so you can sort of see, where is it? Right. You can sort of see here, right? There's a whole bunch of these. They're sort of interconnected with each other. These two, especially the ambiguity function and the Wigner distribution, are two Fourier transforms away from each other. So they're all connected. So things that you do in one space obviously have resultant effects in the other space. And so, yeah, just to sort of see what happens when we apply this path integral methodology to the ambiguity function, or what happens if you go back and forth in that just kind of transforming back and forth between the two. When you apply some math to one, how does that affect the other? And then can you use that to say anything coherent about the engineering spaces that use ambiguity functions to define their capabilities, right? Usually in radar systems, but other kinds of communications and sensing systems also use ambiguity function. It's not restricted just there, but yeah, so that's kind of like the overarching goal. And I've had this goal for a while, and Popo, I know you've heard me go back and forth on this ad infinitum, and so my goal is to not rehash all of this again and start from scratch. However, what I do want to do is start to be methodical about actually progressing this and not just sort of screwing around with it, right? Because I've gone through this paper like 3 times now, I think, twice or 3 times. And so now it's going to be extracting the stuff from this paper, extracting the stuff from the path integration papers to understand them, and just trying to combine them together. So that's the goal, right? Is to actually get somewhere with this sort of endeavor. And so what I'm going to do is, Popo, I don't know if you're here for this. I've sort of put together a schedule. So what's going to happen is every Thursday morning, so between either at 11:30 or noon Eastern Standard Time, depending on what's going on, those are going to be the streams that are dedicated specifically to this. And then I'm also going to stream on Sundays and Tuesdays, but those will be other types of streams, right? Sundays are going to be Sunday morning papers, where we go just kind of run through a specific paper rather than having a goal. And that could be math, it could be philosophy, that could be physics, it could be any other paper you come up with that you decide you want to throw my way for us to go in. Last time when we did the philosophy paper, someone came in and gave some suggestions, so we might go through some of those. I just want to kind of have fun in different areas of the academic literature that just sort of explore things that are of interest to people, right? And then Tuesdays are going to be sort of a catch-all day when we do something. It'll be in the evenings. We'll do something a little less intellectually demanding, just sort of screw around and maybe play some games or do some reading, something like that, right? Anyway, so for why am I getting whoops? That's weird. Dude, I just had that thing where you get like the phantom phone vibration. I could have sworn that I just had my phone vibrate in my pocket, and then I looked up and my phone is sitting on my desk. So that was cool. Anyway, so yeah, so the goal with this is we're gonna hop around this a little bit, kind of just touch on this a little. and extract the important pieces that we need. That's really what we're looking at, right? I also did want to explain for those who don't necessarily have a background in this. I did want to do a brief explanation of Fourier transforms. Popo, if you want to take a rest, you've seen this any number of times. So to do this, we're gonna get my mouse over into the right area so we can see what's going on. Okay, we've got this. And now we are going to zoom in a bunch. All right. So we're going to zoom into this. So briefly, here's how you can think of what a Fourier transform is. A Fourier transform is, first conceptually, is one of a large number of different ways that you can break one function down into a lot of little other functions, right? So you can do this with derivatives, right? You can look at how things are changing and then how things are accelerating and do all these sorts of things to help you define a function. And that's a Taylor expansion, which is kind of just looking at a series of different derivatives of a function. It tells you what's going on around a point, right? It tells you how the function is changing around a point. And then if you were to take that and extend that across all points on your curve, you could redefine the curve in that way. In this case, what we're doing is ideally we're looking at some waveform S of t. So this is something that has... This works best with oscillatory functions. What do I mean by an oscillatory function? That means S of t1 equals S of t naught, right? And then there's probably some S of t2 that equals S of t naught. So it's hitting the same points over and over and over again, right? So the simplest way to think of this is a sine function, right? A sine function does what? It goes up, down, up, right? It's constantly doing it, and then it goes and does it again and again and again and again. It just goes on forever, right? If you just look at, like, sine of x, it's literally just going between -1 and 1 and going up and down and up and down. It's what you're actually doing. If you want to think of it this way, if you were to have a circle, right? And let's say you have a point on that circle, and that point is going around the circle, and you were to map, I think sine's what, the y position? If you were to map the where this is in y, right? So if I look at this position, and as it goes up, it's going to go up in y, right? Until it gets to this point, and then starts going back down in y, and then it's going to go all the way down to here, right? And then it's going to come back up to where it was before, so it's going to go back up to here, and then it's going to do that again, and then the second go around, right? And doop, doop. There you go. This is the sine function. The cosine function is it's moving in, if you were to map its movement in x, right? Literally all it is. So it's going round and round and round in a circle. This is why sines and cosines are connected to circles. So it's just this oscillatory function, right? You can take that. Now something like this, if this this dot is just rotating at a constant speed, that means this frequency is going to remain constant. In other words, you can keep time to this, right? There's a certain, it's going to do a certain number of revolutions per second. It's going to say constant at that number. That's, that's easy to write down. It's just a or I'm sorry, we said this was sine function, whatever. Cosine is just this one. A cosine t, right? Where t is the amount of time that you're looking at. It's going to look something like this, right? And so that'd be, this is at a and minus a, right? That's easy. But what happens if I take this and I add to it something that's going around in a circle twice as fast? Right? So now it's going this in the amount of space that this is happening, right? So now it's going to be, what was it? 2 pi ft. So f is going to be, so now you're going to have, so that's 1/2, right? So it's going to be, plus a cosine t over 2, right? Because its frequency is 1/2. I'm sorry, its frequency is, yes, it's no, sorry, its period is 1/2. Its frequency is double. A cosine 2t. I'm doing a good job here. Look at me do a good job. It's so good. Oh my goodness. Cosine, because it happens faster. 2t. Oops. Why are you freaking slow? Thank you. All right, a cosine 2t. So now we have, this is going twice as fast. And you could, add all these together. And then if you were to combine these, you'd end up with some intermediary signal. Hey, Toast. How's it going? So these are oscillating functions. So in other words, they're just functions. These are just normal cosine functions. They start someplace, they end the same place, right? And then they do it over and over and over and over and over again. Well, it turns out almost any function can be broken down into an infinite sum of these guys, right? Where they might have different amplitudes, so it might be A1 and A2. This one might be bigger, this one might be smaller. But you can just add a bunch of these up. Best of luck. It's always fun when someone hands you something. It's like, here you go. Learn this. What? I expect something out of this in 2 days. Those are always great times. So we're just going over basics of like cosines and sines. And so, right. So, if you were to look at, oh, I wonder if I could do this. Hold on. Waveform. Oh, what is it? It's it's adding to square wave. Yeah, I saw. I managed to hop into Gothic stream for a little bit. It was good to see him there. Yeah, here we go. So I'm just gonna hop, just to illustrate this, I am going to hop this over for a second to what is this under? Yeah, Wikipedia. No. Where are you? Liberwolf. Twitch. No, it should be Fourier series. What's going on? Okay. Say, let's just download this image and do it that way. Okay. Downloads. We open this up. All right, we're gonna zoom in, and then we're gonna put this on stream so you can see what's going on. So this does a very good job of really. So this does a very good job of showing how you can combine waves. All right. So this kind of shows you what happens when you add a bunch of waves together and you can make a different function, right? So this is adding a bunch of sines and cosines together to build a square wave out of it, right? So now let's say you have a square wave and you want to know what all of these sines and cosines are that are making up this square wave. That's where a Fourier transform helps. What a Fourier transform is going to do is it's going to give you the sum of all of the functions that make up, or all of the sines and cosine functions that make up some other function, right? So you can take a signal that you don't know what it's doing and break it apart into its frequency components, and it'll tell you what frequency they are and how much of that frequency is in it. Now, for any finite function, right? So something that's not continuing on forever, if you're trying to add a bunch of infinite functions, sines and cosines, to get a finite function, you're actually going to technically need an infinite number of them. Now their amplitudes eventually drop off to the point where they don't matter anymore and you don't have to worry about it. But, so usually you'll take the first few that you care about. But if you do have a infinite or essentially infinite, series, you can get an exact representation of it. And so for anything oscillating like an audio wave or a radio wave or one of these kinds of things, you can actually break it down into the specific frequencies that make it up, right? And you can plot out the amplitude of those frequencies, right? So you'll get a plot that looks like frequency, and it might be, 1 hertz and 2 hertz or 1 kilohertz or 1 gigahertz, whatever it might be, etc., right? And you might have this much of this one and this much of this one and a little bit of this one, right? This gives you information about your signal that you need if you want to recreate your signal. And it can be very important. And this is very good if I have a static symbol. We'll get that in a second. So how do you actually get this, this set of, how do you actually go into the frequency space where you're looking at things at frequencies? You do it this way. This is the formula of a Fourier transform, right? We're integrating from negative infinity to infinity of our signal here, right? This is the function in time space that we want to transform into a function in frequency space, right? We want to know what the frequencies are. We have some signal that's changing in time, and we want to know the frequencies that make it up. So we're going from time space, that's the terminology that's used, into frequency space, right? we're going to go across, if you notice, for all time, we're integrating with respect to t, right? We're essentially summing over all time. And we are multiplying by this complex exponential 2 pi I f t, right? And what will happen is this now, when you integrate over time, you're so if you have a function, right? If I have some function f of x, y, and I were, that's, if you think about it, what that can do is that's a function that's varying over x and y, right? So it's existing somewhere in this space. If I were to take some function in this space and add up all of its components in y and realize that it's a 2, right? This is the sum of everything. The only thing it can do now is vary in x, right? Because I've taken all these y components at each point and I've just kind of added them together and I've got 2. I've summed them all up. They're just some number now. They're not a variable anymore. So now I just have a function that varies over x and doesn't vary over y. An integral is a big old sum, right? So when I integrate from -infinity to infinity, say dx, that means I'm taking the sum of all the x values, right? And so now I'm going to end up with some number times some function of y, right? The x, it's no longer a function of x because I've evaluated all the function of x. I've integrated it out and it's all bound up in this. It's now just a function of y, right? So that's what we're doing here. We're integrating over t, so the result is not going to be a function of t. We're taking a definite integral from -infinity to infinity over t. So the resultant is only going to be a function of the remaining variable, which is f, right? So now we have a function of frequency that is defined by this term here, right? So it's a complex exponential, which means it's oscillating. Again, we can go back to Euler's formula, e to the I theta equals cos theta plus I sine theta. If we're using this formula, what this means is that there is a deep connection between oscillating functions and exponentials with an I, right, in the exponent. That means that you can describe an oscillating function either as sums of sines and cosines or as sums of complex exponentials. And so it happens to be that complex exponentials are really easy to differentiate and integrate. So typically, we'll want to talk about things in terms of e to the I theta instead of cosine theta plus I sine theta. It just makes the math come out easier. There's a whole bunch of there's a whole bunch of mathematics. It just comes out a lot easier if you use exponential functions instead. It's just makes life easy. So what that means is that we replace any cosine or sine with some complex exponential function. So when it comes to this Fourier transform that we were talking about, all that means is that we're retaining the oscillatory nature of our original signal, right? And we're coming up with some function of frequency. That's the background, right? All very well and good. If we have a signal in time, we know that we can transform it into a function of frequency, and we can look at that signal in frequency space instead of in time space, which is all very well and good, but there's a problem there, right? What I've said is we have this at capital S, right? The Fourier transform of our signal is no longer a function of time. We are integrating it over all time. We don't know how that function is going to change. Let's say we are looking at an audio signal. That audio signal is changing in time, right? As like if we looked at the audio signal of my voice as I'm speaking, I'm saying different things. I'm not saying the same thing over time, right? I'm saying different things at different times. And so I don't just want to know, I don't want to after the fact have taken, I could take a recording of my entire stream, right? All of the audio from my stream. And afterwards, after that stream, I could do this and find out what the frequency content is across my entire stream, right? And it would be very accurate. But it's not very specific. What do I mean by that? What if I start talking really high in one part of the stream? I start talking really low in another part of the stream. Those are different frequency ranges. So at one time, my frequencies might be really high. At another time, my frequencies might be really low. So if I want to take into account things that happen within a small point in time of my signal, I can't just do this integration because all of that information is going to be lost. So what I can do is I can chunk up my signal and say, all right, I'm going to look at one piece of my signal here. That's kind of what we've got in this image over here. I'm going to take a window and I'm going to look at everything in this window. And then I'm going to shift the window over, right? So as the signal comes in, this window, I add up my signal for a certain amount of time. I do this Fourier transform integral for this portion. I find out what the frequency content is of this portion, and then I move the window over to the next portion, right? Now I can say, well, what's going on here is different than what's going on here. And so my accuracy in time will change as I increase or decrease the length of this window. I'm always going to be trading off to where my accuracy and frequency space is going to be inversely proportional to the length of the window. The longer the window, it's going to directly. The accuracy in time is indirectly proportional to the length of the window, right? So if the length of the window is some delta t, right? I can now only find events that are larger than delta t, right? This becomes kind of my my pixel size. You can think of it like that, right? Delta t becomes my pixel size in time, so I can identify a color range, an audio range, whatever happening in this time period, and I can differentiate that from an audio range happening in this time period. So this could, going back to the pixel analogy, this pixel could be one color, this pixel could be another color. And I can fit more pixels if I make this delta t shorter, right? In the same way that you're doing that with an image. My entire image is 1 pixel. I have a single color. If I break my pixel down, or my image down to 4 pixels, I can have color 1, 2, 3, and 4. And the more I break it down, the more precision I can have, so I can be more accurate with what's going on in here, right? So the shorter this delta t, the smaller time events I can resolve, right? So if there's an event that happens over multiple of these, I can actually almost image it, right? I can kind of see what's going on across multiple of these, quote, pixels, time pixels, if you want to call them that. And I can start to see these things, but I can't see anything smaller than 1 pixel, right? Anything smaller than that is going to be just averaged out over the course of that time. However, my frequency resolution, so in other words, what frequencies I can differentiate between these, can I tell the difference between f and f plus delta f, that is directly related to this length of time, right? So the longer this length of time, the smaller this delta f that I can resolve. So now my pixels in frequency space are smaller if my time is extended, but my pixels in time space are larger. So I'm always doing this trade-off. I'm always either being more accurate in frequency space or I'm being more accurate in time space. One of those, right? The more, because these are two different metrics on the same thing, right? They're still looking at the same signal. I'm always trading off between the two. And they're just different ways of viewing my signal that highlight different aspects of what's going on, right? Okay. So the point being, though, that we can say, we're willing to take a hit, and we're willing to say, all right, I'm going to do a balance between these two options, right? I'm going to pick some window that's long enough to be accurate, decently accurate in frequency space for anything that I think that I might need, and it's going to be short enough that it should pick up most of the events happening in time space, right? I'm going to try and pick what that is, and that's going to vary with depending on what you're looking at, right? If you're looking at something like audio, which varies at a certain speed, right? You're looking at things that change over tenths to hundredths of seconds, right? You're looking at hertz up to kilohertz kind of frequency ranges. If you're looking at, I don't know, a Wi-Fi signal, that's sitting up at 2.5 or 5 gigahertz, right? Now you have a different range that you're looking at in terms of your time frequency. So this window is going to change just depending on what your application is. But regardless, whoa, what the heck just happened? Oh, sorry about that. Hold on. One moment. Why did you do that? What? My tablet just killed itself. I know, right? Womp womp. Womp womp. Hello, do you want to turn back on? Okay, it's turning on. Oh, my tablet just killed itself for a second. You couldn't see it on screen, but all of a sudden I couldn't do anything on my notepad there. Okay. So why am I going through all of this shenanigans? Because what I really care about is this combination of time frequency, ways of displaying time and frequency. For example, let's say I am an audio engineer, right? And I am looking at some audio that's coming through and it's doing this and it's doing this, or it's going faster and slower and blah, 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 right? And it's doing this for a long time. It kind of, right? So a lot of the numerical method stuff falls into similar sorts of categories, right? You're doing a lot of functional expansions of things. You're looking at different ways that you're trying to look at, some function or something, even though you can't fully get there in, like, say if you're using a computer, you're going to end up with floating point errors at some point, and so your approximations are going to fall apart. So you can use these different methods like Newton's method, and which you might remember the name. Okay, well, yeah, that too. Uh if you remember Newton's method, or you remember any of these other methods of function approximation, right? There's a lot of similarities with the math there too. In addition to just the silly note taking, yes, I agree with you. I have more scribbles than PDF. Anyway, right. So what I can do is I can look at something called a spectrum analyzer, right? And so what a spectrum analyzer is going to do is it's just going to convert this. It's literally just going to do a Fourier transform and convert this into frequency space, right? So this will be, I'm looking at the signal in time, and here I'm looking at the signal in frequency, right? Yeah, dude, this stuff, if you don't use it, like if you don't use it, you lose it. Honestly, um, it's easier to relearn the second time around, but you do have to relearn it. Because I did my undergrad, and then I took a break, and then I did my master's degree, and then I took a break, and now I'm doing my PhD. And each time, it's years between these, and so I forget everything. I forget what I forgot, and then I have to run back into it and learn it again. And so, which is actually one reason why I'm doing these streams, is so that I can continuously refresh myself about these things that I care about, that I want to keep in my mind. So that's why I'm trying to do that in these streams. But yeah, it's amazing how much you forget, and then you start running into it again. You're like, oh, that looks sort of familiar. Anyway, so yeah, so you have this literal piece of test equipment in a lab called a spectrum analyzer that's just doing a Fourier transform on the signal that's coming in, and it's plotting it, right? And you can, if you do anything with radios, if you do anything with audio, if you do anything that's sitting in this sort of wave component kind of area, you'll see these. They're literal just electronic test equipment that you'll see. Usually, these test equipments will have something called a waterfall, right? And what the waterfall is doing is it's going from this into a 2D plot, a 2D like heat map plot, right? So it's going, usually it's like frequency, and this is time, and time is increasing in this direction. Cool. We've got another ad in here. Womp. Let's go. Ah, shoot, I'm gonna have to log in. 1 second. We're gonna do some quick moderation. Do. Sorry about the... Sorry about that. Yep. You may. 1 second. Hey guys, I will be right back. Sorry about that. Oh my goodness. Ah, man. I apologize for that. Where's mine? Now here, and then 1, 2. Cool. There we go. Okay. Sorry about that. Yeah, we had a whole bunch of people in the neighbor's backyard. Turns out they're like doing housing inspection stuff. I don't know. Anyway. There we are, back to it. Okay. So, I'm so sorry for that interruption. Back to this, right? So, I was explaining the waterfall, right? Because this is really getting towards what we're interested in, is this. So this is time. So you'll see the actual screen looks like it's going, it's like changing, moving up, right? And so each of these is split into those time windows that I talked about over here, right? It's split into these time windows. And so in this time window, I'm going to have a certain set of frequency content, right? That's going to be, usually it's different colors, right? And it'll be different, split into my different frequencies. And then you'll see the next time step, right? Is this one. And the next time step is this one. And the next time step is this one. And then as time progresses, right, they slide up the display. This is what's called a waterfall plot, right? Typically, they're very brightly colored. And what they're doing is they're telling you how that frequency content changes over time. This is a 2D time frequency plot. That's what this is, right? And these are the types of things that are like Wigner distributions, which is the mathematical construction that we're going to be trying to operate with, are essentially a type of time frequency plot, right? This is actually a spectrum analyzer plot. What do they call it here? Okay, a spectrogram. This is a spectrogram plot, right? It is a type of time frequency plot. It is a 2D plot. Each point in that two-dimensional plot has a value associated with it. It's actually really a 3D plot, but it's a 2D heat map is usually how they're shown. And so they are a function of time on one axis and frequency on the other axis, right? And so what it's doing is it's looking at different windows in time on each row, right? Each row is a different window in time, and then each column is a different frequency. All right, so we have now a 2D space where I'm chunking off sections of time. I'm taking the Fourier transform of them to find the frequency content in that section of time, and I'm plotting them. Cool. How do I represent something like that mathematically? Valid question. Let's take a look at this without some of the markings around it. And we can kind of start getting an idea of what's going on here, right? This, if you notice, looks a whole lot like a Fourier transform, right? It's literally, all right, we've got this, here's S of some variable tau, right? We have e to the 2 pi I f tau, and we're integrating it from negative infinity to infinity d tau. That's literally a Fourier transform, this section. But we have this little thing added here, and this is W of tau minus t, right? This is what's added to make the spectrogram. And what is W of tau minus t? It is a window function. What? The window function is essentially giving you these slices. A window function is a step function. It looks like this. It's 0. It's 0 over here, and it's 1 over here. So if I multiply some other function by this, anything over here is going to go to 0, and anything in here inside the window is unchanged, right? So I end up with 0, function, 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 0, right? And now we're taking this window here and we're sliding it along our function. So this dummy variable tau that you're integrating across is telling you that you're sliding this window across the entire time of this function, right? And so you're looking at different chunks of the function over time. You're right, as tau advances, the location of this function, which is determined by this t tau minus t, right? That's telling you it's moving along in the time axis along here, right? So it's just, you can imagine the entire function here is stationary, and you're taking this window and you're sliding the window along, and you're looking at what's inside the window at any point in time, right? And if you were to plot that as a two-dimensional plot, you would get a spectrogram. And this is what's plotted, again, in a lot of test equipment that you'll see. It literally says spectrogram, and you hit a button, and it shows you the spectrogram of what's going on in the radio signal or the audio or whatever it might be, right? Optics, anything that's got a wave, you can build a spectrogram of. So it's just a way of plotting, of visualizing, of combining the time information and the frequency information all in one place. That's all it's doing. It's combining time and frequency information in one place. Okay. Now, it turns out that you can play a game with this type of function, with this kind of setup, where you can start messing around with these functions in here, right? And there's a whole class of time frequency distributions that are within this class that kind of all act in somewhat the same way, but they have something instead of the window function. This is where the Wigner distribution comes into play. And this is how it's defined. We're going to have to go into a little bit of a divergence here to explain what's going on. All right. So, again, this sits in the same kind of class of functions as the Fourier transform, as the spectrogram. We're going to end up with a two-dimensional function at the end of it, right? That's a function of time and a function of frequency in the same way it was for the spectrogram. So that part is all the same. But what's different is what's going on in the middle, right? We have this S tilde function here, which, can you see that it's S tilde? Yeah, you can see that it's S tilde. And we have one part that is advanced or that's delayed by tau over 2, and one part that's advanced by tau over 2. And then we're shifting that. So this is kind of our window, if you will, from negative tau over 2 to tau over 2. It's sort of like a window, but that window is like built into these S tilde functions, right? And we have this star symbol here. This is the complex conjugate. Complex conjugate, all it does, the only thing complex conjugate does is it takes I and turns it into negative I. So if we had e to the negative 2 pi I ft, it's now e to the negative 2 pi negative I ft. And then the negatives would cancel out, right? That's all it's doing. It's just, which by the way, if you multiply these by each other, you'd get 0, e to the 0, which is 1. Which is important. That's really what it's doing. That's why the complex conjugate, right? Because if I multiply, let me explain what the complex conjugate is doing. If I have a complex number, a plus bi, and I multiply this by a minus bi, and I FOIL all of this out, first, inner, outer, last, I'm going to end up with, what? Let's see. A squared plus abi minus abi minus bi squared, right? Plus, these cancel out. You end up with a squared minus bi squared. I squared is -1, so that equals a squared plus b squared. We've removed the imaginary portion of our okay, I'll be here for a little bit. So what we've done by multiplying by the complex conjugate, we've removed the imaginary portion, right? That's what we've done. And so that's what's going on here. So that's the complex conjugate piece. The other piece is what's called the analytic signal, which is formed by a Hilbert transformation. What the heck is that? Well, let me tell you. Let me tell you something fun. These Fourier transforms mathematically are inherently complex natured entities, right? By definition, we have complex numbers in our Fourier transform. We just do. But our original signal is a real valued signal, right? It's just a real value that's varying in time, right? This is just a real valued signal. So what happened as a result of that, if we were to Fourier transform this, we end up with a kind of a mathematical artifact built in, right? Where this is 0 hertz, right? And so let's say we have a signal that's like this, right? It's got these 3 frequencies in it. This one's the highest, and then it goes down as you go up in frequency. If you were to look at the actual Fourier transform of this, it would actually look like this. It's mirrored across 0 hertz. These are negative frequencies. Physically, that makes no sense. What is a -1 cycle per second? That doesn't really, right? Physically doesn't make sense. But this is an artifact of the mathematics that goes into doing the Fourier transform. This is why mathematics is a language about that we use to discuss reality, right? But it still has some quirks in the same way that when we try and write a poem about a sunset, our poem is going to be very exact in certain ways and very inexact in other ways. Right? There's going to be artifacts of the language that the poem is made up of that's going to make it better or worse at describing different aspects of it, right? Maybe it's better at describing the emotional content or the connection to memory or the connection to love or whatever it might be, right? But it's worse at describing. The poem's not going to be very good if you want to find out what the frequency content of the light in the sky is, right? You're probably not going to be as good at that. I mean, you could, right? You could describe it, but it's going to be kind of clunky and awkward, right? You're going to end up with a lot of linguistic artifacts that go into your description. And the same kind of thing is happening here, but with mathematics, right? We're making a mathematical description of a certain aspect of this real signal that's really varying over time, right? This is, if this is an audio signal, this might be pressure. This is time, right? You're literally measuring actual pressure, atmospheric pressures at different times. And the, so this is the physical compression and expansion of the air particles in time, right? That's what you're looking at, is the varying density of the air in time. The frequency is one step removed from this, right? The frequency is telling you information about characteristics of this signal. So when we use this mathematical description, this mathematical language, we end up with these artifacts. Now, what you can decide to do is say, well, I really care more about this than I care about this. So I'd rather have the mathematical artifact sitting on this side than sitting on this side. Right? So instead of using this description, I'm going to add an imaginary component to this that's going to cancel out these negative frequencies so that when I do the Fourier transform, those negative frequencies all drop away. Right? So now this looks more physical, but this looks less physical. I'm just playing a game with where do I want those artifacts to sit? What's more important to me? Right? And I'll have the artifact sit in the place that's less important to me. That's all you're doing, right? So if you're clever about it and you think about it, what you want is essentially things that kind of do this, right? Because you want this to cancel out to 0. And to do that, you're doing that is what the Hilbert transformation is, right? Let's go down to it and erase all the notes that are getting in the way. All this Hilbert transformation is you're trading off. Hello. You're trading off. So what I was saying was, because mathematics is like a linguistic description of the physical thing that's going on, in the same way that you use the analogy I said was using poetry to describe a sunset, right? You'll be very accurate with certain things and very inaccurate with other things as you use that poetic description, right? You might be very accurate about your feelings, the connections it makes, things like that internally to yourself. But you might be very inaccurate about the physical description of the sunset. The same thing is true of mathematics. So when I do this Fourier transform, I end up with these mathematical artifacts that are sitting in this frequency space representation of my real signal. That's really a measure of how real pressure is really changing over time, right? This is an actual real signal, but I'm going to end up with these mathematical artifacts when I apply this Fourier transform. Now, I don't really care too much because it does also give me useful information about the characteristics of my signal. But if I'm more interested in this representation than in this representation, I can be clever and move my mathematical artifacts up to here and remove them from down here, right? And that's what this what's called a Hilbert transform, that's all it's doing. It's saying, I'm kind of taking a step back and looking at my signal and say, well, if I add this imaginary component to my real signal, then when I do the Fourier transform, it'll create negatives where all those negative frequency components are, and the negative frequency components will all drop away, right? They'll all subtract out. That's all it's doing. You don't need to go into the guts of it. All you need to know is by applying this, you're just moving the mathematical artifact from the Fourier space into the time space, right? So now I'm just looking at this other signal that's now a complex signal in time to give a more accurate representation when I look at it in frequency space. So that's all this is doing, right? And then the plus tau over 2 and minus tau over 2, this is just shifting in the same way we shifted the window back and forth across the whole signal, right? This is just a dummy variable for time. I'm just saying I'm moving this window essentially over time, right? I'm scanning this window back and forth over time. So again, this is just another way, this Wigner distribution, in the same way that the spectrogram, that you can push the button on your spectrum analyzer to look at the waterfall display, right, of what my frequency content is at any point in time and how that's changing over time. This is just another way of doing the same kind of thing. It's a representation of my signal in a time and frequency space. It's just a different time frequency space from the spectrogram. And it's different because you build it in a different way. These whole class of functions are important. And the reason these class of functions are important is, I'm going to hop over here. He's just talking about different characteristics of the Wigner function. Or the Wigner distribution. We don't need to really go into them. They abide by certain rules, et cetera, et cetera. It doesn't really matter, right? A lot of these come directly out of the rules of the Fourier transform. But we are interested in this piece over here. Okay. So what is this? This might seem to come out of nowhere. What the heck is this? What am I talking about? Right? This is another let's see. Right. This is another 2D time frequency representation that looks really similar to the Wigner distribution that we just looked at, but is a little bit different. Because what I've done is I've gone into a different set of variables. I'm not looking at time and frequency anymore. I'm looking at something called nu and tau. What is nu and tau? Let me explain. And after we go through this back and forth interaction, we'll probably end there for today, because that'll set up this portion of what we're looking at, and then we'll try and extract the specifics next time. We'll take one more look at this next Thursday to extract specifics that we're going to take out of this paper that we're going to look at in combination when we're going to apply it to, or we're going to apply path integration to this. We'll take out the bits and pieces that we care about. But let me just go through this relationship, because this relationship is really key to this whole thing. Right. So let's say, and this might seem to come out of nowhere, let's say I'm working with a radar. I have a radar, and my radar's here, and I have an airplane that I'm looking at here. And for those of you who came to the little radar stream, you'll remember this. And I send out some signal, right? And I bounce it off my airplane, and I look at the return. What are the two things I'm looking for? One is the time delay, right? How long it took to go out and back, because that gives me a range. Technically delta t over 2, right? Because the time is the out and back time, right? So time delay is one thing I care about. And the other thing I care about is Doppler. In other words, if this is coming towards or away from the radar, right, this is going to see a F plus delta F or an F minus delta F based on how this airplane is moving, right? I'm going to get the same thing you get with an ambulance coming towards you and then going away. You get the Doppler effect going on there. This Doppler effect happens on the signal, and this correlates to the velocity of the aircraft towards or away from my radar system, right? So I care about range, so time delay, and I care about Doppler. Those are the two pieces that I care about, right? Which is kind of like it's a F plus delta F, right? It's this change in frequency. So if you look at it, we kind of have something that cares about time, and we kind of have something that cares about frequency, but they're a little shifted, right? We're talking about range and Doppler, or time delay and Doppler. But there's still time and frequency associated. They're still adjacent, but they're just not exactly the same. So I can what I can do is I can look at, instead of looking at time and frequency, I'm going to look at Doppler and frequency. Oop. And and time delay, right? So I'm going to say this is going to be F plus 2 delta F. This is going to be F plus delta F. And this is going to be F. And this is going to be F minus delta F. And this is going to be F minus 2 delta F. And then I'm going to look at time. So what's going to happen is, ideally, right, if I had an ideal signal and I was looking at this perfectly, right, at a certain delta t that corresponds to the distance to the aircraft, and at a certain delta f that corresponds to the velocity towards, or the radial velocity, right, towards or away from the radar, I'll get a spike here, and everything else will be pretty low, right? I'll have some noise, I'll have some junk here, but in general, I'll have a spike here and like this, right? So this is called the ambiguity function. And it's really a measure, it measures kind of what your resolution is in time and Doppler, right? Because this here is going to be your resolution. Again, you can't resolve anything that's closer than these two, right? Than these spots here. So in the same way that's like the pixel resolution again, you're doing the same thing. It's another pixel resolution kind of thing, right? You've got your 2D pixels, and you can resolve things that are in the 2D pixels, and you can't resolve things that are smaller than 2D pixels, right? So that's why it's called an ambiguity function, because it's telling you what your uncertainty is in range and Doppler, right? But again, this is just another one of those same sorts of functions. It's just a two-dimensional way of representing frequency and time. It's the same thing as the Wigner distribution, or it's very similar to the Wigner distribution. And how similar is it? It's so similar that you can actually just transform back and forth between them. It turns out, if I just do a two-dimensional Fourier transform, one to get change from nu to t, the other to change from f to tau, I can go from A to P, right? I can go from my ambiguity function to my Wigner distribution, and from my Wigner distribution back to the ambiguity function through transform and inverse transform, right? Inverse transform or inverse Fourier transform to go back and forth between the two. That's the relationship that's important. Okay? That's the relationship that we're going to be using. Because we're going to be looking at how quantum mechanics does stuff in this space, and we're going to ask what that means if we want to look at radar signals in this space. And the answer is, I have no idea, and I haven't seen anyone else do it. So that's why this is not saying that it hasn't been done. Someone might have done it, and I just haven't found the papers. Totally possible. In my investigations, I haven't found it. But that's the goal. That's the target. That's what we're trying to do. Can we say anything about how the techniques applied in this space affect something in this space? Can we use these techniques in a similar way? Now, chances are the answer will be yes, you can use them. It's mathematically really complicated and you don't get anything new out of it. I would say that's most likely the chance that'll happen, right? There is definitely this connection. So there is a relationship between what happens in one and what happens in the other. So you definitely can apply it. Chances are it's not going to give you anything useful. But we don't know that in advance. Or I don't know that. Maybe you know that. I don't know that. So that's what we're going to explore. And so these series of streams that are happening on Thursday are going to be exploring this piece here, right? This relationship between these types of functions and what happens when we apply math to one and how that changes the other. And if we can use that to start saying something different about one side or the other side, right? Maybe there's something in the math that's applied to the ambiguity function. Although the ambiguity function is usually just used kind of as a metric rather than a function space in which you do math, compared to like Wigner distribution, which is a little different. But I don't know, right? I mean, there's clearly a relationship. Like they're just Fourier transforms away from each other. They're the same thing in different clothes. But what's going to happen when we look to see what this relationship looks like when we do this path integration technique that's done in quantum mechanics? That's the goal. That's the target. That's what these Thursday streams are going to be about. If you have any specific questions after the fact of this, you want me to go more in depth in the next one of these streams into one of these subjects or some area of the subject of how we do something in this area, let me know. Ping me on Discord, and we can try and deep dive either in one of these, or if it doesn't fit into one of these streams, we can fit it into one of the other streams that we do. Maybe on a Thursday we can go in, or on a Tuesday we can go into it. Yeah, so if something is confusing you, if I say something wrong or something doesn't make sense, you're like, I don't think it works that way, let me know. I'm in a lot of ways learning this as I go, so there's a very decent chance that I'm going to make mistakes. Did you ever do population models? Population models of what? I mean, yes, you can use these methods for a lot of different types of things. Right? They're just math. They're Lakota World. I don't know that one off the top of my head. I would have to go look it up. But you can use this sort of representation, right? So you can use like a Wigner distribution representation, or a what, I keep forgetting the name of it, the spectrogram representation of anything that has the type of statistics that you can apply frequency terms to, right? So anything that's kind of has this any sort of oscillatory nature to it, where Fourier transforms are really are applicable. You could probably, for things that aren't oscillatory in the same way, you can do things like wavelet transforms. There's sort of a bounded type of Fourier transform that work for things that are it applies a little better to other types of functions. I haven't messed with them too much, but I know that they exist, and I've sort of poked at them a little. So there are other ways to do it. But yeah, you can, if you have, so if you want to know like population changes over time, over seasons, right, over years, and you're looking at how the population changes, evolves based on different influences and things like that, you can absolutely break it down in this way. I have never done that myself, but that is certainly something that this is, these sorts of mathematical constructions can be useful for, right? They're not necessarily. So here's the other thing. We want to apply these in areas where they're useful, where they'll tell us something about what's going on. You can infinitely turn mathematical cranks and not get anything useful out of it if you want to, right? In the same way you can talk infinitely about something and never say a useful damn thing. So you have to look at the characteristics of what you're trying to understand about a population, or how a population is changing over time, those sorts of things, and ask, does this give me information that's new? Does representing it in this way show me something that I wouldn't have been able to see, or would have been hidden in the details? You know, a lot of this stuff is like, if you're looking at the frequency of a signal, right, it's hidden in the noise. It's hard to actually pull apart and see if you're just looking at the time evolution of the signal, unless the signal is very, very simple. So when you do the Fourier transform, all you're doing is you're taking certain aspects of it and you're highlighting it in different ways mathematically, right? And in the case of a signal that I want to, say, embed information on, or I want to figure out a way to save that signal into computer memory, right? It's a lot easier for me to just break it apart into the frequency content and just save those frequency values, right? That might be less memory than saving the time representation of it. And then I can reproduce to a certain error, right? Depending on how accurately I'm doing this. To a certain error, I can reproduce the original signal. And so, yeah, so it depends what you're trying to get out of it, what you're trying to do with that data. So I don't personally know what the Lotka-Volterra population models are, but I wouldn't be surprised. And if you're interested in us going over, if you have a paper, actually, this, if you have a paper that explains these, and you think this is something that would be interesting to go over, send me the paper, and we can add it to one of our Sunday morning papers, and we could go through it then. Yeah, that's the other thing. If there's a paper, and it doesn't have to be in math or physics, it can be philosophy, it can be literature, it can be computer science, it could be whatever. I will do my best to make heads and or tails of it in a Sunday morning paper sometime if you express interest in it. So please feel free to reach out with Don't mind like populations. Yeah. I bet you we could do cool stuff with this. And we could write a couple of Python scripts, taking that information in and doing fun stuff with it. It's totally possible. I haven't done that. I know kind of what you're talking about. I haven't done it personally, aside from just toy problems. But I do know what you're talking about, and where you have like the balance with overpopulation and predator population, things like that. Yeah. By all means. And like I said, if you find a good paper that you think is interesting to go through, send it my way and we'll go through it. So anyway, next Thursday, when we do another one of these streams, we're going to use this paper one last time. And what we're going to do is we're going to chunk out the sections that we're going to use for our next steps, right? We're going to look at the different aspects of this. Again, I don't want to deep dive in this paper. I've already done that a couple times. But we do want to make sure that we pull out the things that will be important to us later. So otherwise, I'll let you guys go. Thank you so much for showing up to this, to me, wildly scribbling something that approximates math onto, and yeah. Thank you. I really appreciate it. We will be back. I think the next stream is on Sunday for Sunday morning paper. That will be at, oh geez, what time? I haven't technically set up next week's. I'll send out next week's schedule. Where did I put it? Here we go. Sunday at 10:30 Eastern, we will be doing the next Sunday morning paper. That will be part 2 of our philosophy paper. We'll finish that up. And then we are open for whatever follow-on papers you would like to do. Otherwise, have a good one, and I will see you guys later. Bye.